Welcome to our lecture on the Gauss-Markov setup. Imagine you are building a house. Before you pour the concrete or put up the walls, you need to make sure the ground underneath is solid, level, and will not shift over time. In statistics, when we try to draw a line through data points to make predictions, we are building a mathematical house. The Gauss-Markov setup is exactly that solid ground. Let us explore what this means. Now that we understand the house analogy, let us look at what this setup actually is. The Gauss-Markov setup defines the standard theoretical environment for linear regression models. Real-world data is never perfect, so we always have a random error term representing unpredictable noise. This setup strictly defines how this error term is allowed to behave. Interestingly, it does not require the errors to follow a normal bell-shaped distribution. Instead, it only restricts the average value, the spread, and the independence of these errors. By establishing these boundaries, we guarantee our mathematical methods will work. To formalize this, let us look at the core equation of a linear regression model. Y equals x times beta plus epsilon. Where does this come from? It is the mathematical way of saying our outcome depends on our inputs plus some random noise. Y is the dependent variable, the actual outcome we want to predict. X is the design matrix containing all our known input data. Beta represents the unknown weights, telling us how much each input affects Y. Finally, epsilon is the error vector, containing the random mistakes for every observation. If an input in X increases, Y changes based on beta, but is always nudged slightly by the noise in epsilon. Before we move on to the specific assumptions, let us see this equation with a concrete example. Suppose we want to predict a student's test score based on the number of hours they studied. We have data for 3 students. Student 1 studied 2 hours and scored 50. Student 2 studied 3 hours and scored 60. Student 3 studied 5 hours and scored 80. First, we construct the Y vector. This is simply a vertical column containing the 3 test scores we observed. By organizing them vertically, we prepare them for matrix multiplication. Continuing with our setup, we next construct the design matrix X. The first column is entirely made of the number 1. This acts as a mathematical placeholder for the y-intercept, which is the base score if a student studies 0 hours. The second column contains the actual hours studied by the 3 students. We also define the parameter vector beta. Beta 0 represents the unknown intercept and beta 1 represents the unknown slope, which tells us how much the score increases per hour of study. Our goal in regression is to find the best numbers for this vector. Finally, we define the error vector, epsilon. Each student gets their own specific error term in this vertical list. This represents the random factors affecting their score that we did not measure, like how well they slept the night before. We never know the exact values inside this vector, but we assume they follow the Gauss-Markov rules. By putting these pieces together, we have successfully translated a messy real-world scenario into a clean linear algebra equation. This structured format is exactly what computers use to calculate the final predictions. Now that we have built our model, we must explicitly list the core rules that make up this setup. These are the 5 pillars that keep our mathematical house standing. First, linearity, meaning the model must be a straight line relationship regarding the unknown weights. Second, zero mean errors, meaning individual errors must perfectly average out to 0 over time. Third, homoscedasticity, which means the spread of the errors remains exactly the same. Fourth, no autocorrelation, meaning the error of one point does not influence another. And fifth, no perfect multicollinearity, meaning our inputs are not exact mathematical copies of each other. Let us look closer at the second assumption, the zero mean of errors. The formula is E of epsilon equals 0. Conceptually, this means that the random noise does not systematically push our predictions too high or too low. The symbol E stands for the expected value, which is the theoretical average over the long run. Epsilon is our random error vector, and 0 is a vector of zeros. If the expected value increases above 0, it means our model is consistently overestimating. This rule ensures that positive mistakes and negative mistakes perfectly cancel each other out. To see how this works in practice, let us verify this assumption with an example. A researcher is using a linear model where the error term for each observation is determined by rolling a standard 6-sided die and subtracting 3.5. We need to mathematically verify if this specific error generation process satisfies the zero mean assumption. If it does not, the model will be permanently biased. We start with the standard formula for the expected value of a discrete random variable, which multiplies each possible outcome by its probability and adds them together. Continuing our calculation, we substitute the actual numbers into our expectation formula. We multiply each possible die roll from 1 to 6 by its probability of occurring. Because the die is fair, every single outcome is multiplied by the exact same fraction, 1 divided by 6. By adding all these fractions together, we find the total sum is 21 over 6, which equals 3.5. This means the theoretical average of a standard die roll over an infinite number of rolls is exactly 3.5, which is the mathematical center of gravity. Now we apply this to the error term. We write down the researcher's specific formula, epsilon I equals d minus 3.5. We apply the expected value operator E to both sides. According to the mathematical rules of expectation, the expected value of a variable minus a constant is equal to the expected value of the variable minus that same constant. We substitute our previously calculated expected value of 3.5 and subtract 3.5. The result is exactly 0. This proves the random noise will not systematically bias the predictions, and the researcher can safely proceed. Having verified the zero mean, we move to the next crucial assumptions, variance and independence. The third assumption requires homoscedasticity, which simply means constant variance. The spread of the errors must remain exactly the same no matter what the input values are. The fourth assumption requires no autocorrelation, meaning the error of one data point has absolutely no connection to the error of any other data point. If we ignore these and use data with highly correlated errors, our models will report false confidence, leading to disastrous decisions. We can express both of these rules in one elegant matrix statement. The formula is the covariance of epsilon equals sigma square times I. Conceptually, this matrix measures how the errors vary and relate to each other. The term cov epsilon represents the covariance matrix. Sigma squared is a single unknown constant number representing the variance or the spread of the noise. The symbol I is the identity matrix. The ones on the diagonal mean every error has the exact same spread, and the zeros everywhere else mean no two errors are correlated. If sigma squared increases, the overall noise in our model increases. This diagram perfectly illustrates the concept of homoscedasticity, which is often the hardest assumption to visualize. On the left, you see the valid setup. Notice how the vertical spread of the dots remains exactly the same across the entire horizontal axis, looking like a straight tunnel. This is what the Gauss-Markov setup requires. On the right, the spread gets wider as we move along the axis, shaped like a megaphone. This violates our setup because the noise is no longer constant, meaning we cannot trust our predictions equally across all values. You might be wondering why we are so strict about these 5 specific assumptions. The reason is a famous mathematical proof called the Gauss-Markov theorem. These assumptions are exactly what the theorem needs to prove that ordinary least squares, or OLS, is the best linear unbiased estimator, known as BLUE. OLS is our standard method for drawing the line of best fit. Blue means that out of all possible unbiased ways to draw that line, OLS guarantees the smallest possible error. If even one assumption fails, OLS loses its best status. To summarize, the Gauss-Markov setup is a strict set of mathematical rules governing the behavior of linear models and their random errors. It is the absolute bedrock of modern statistical modeling and machine learning. Remember the 5 pillars: linearity, zero mean errors, constant variance, independent errors, and no perfect overlap in the input data. By strictly checking these conditions before trusting a model, we guarantee that our standard estimation techniques will yield the most accurate and unbiased results possible. You now understand the solid ground upon which all linear regression is built.